So now, in view of this, again we will try and give you a hint about the maximum principle, how it is somehow hiding within. Okay, let's take a closer look at this. Let's go back to our Hamiltonian, the way we understand it. So suppose we have the Hamiltonian evaluated for x, y, y prime and p. P is the momentum. Okay. So this is for that particular choice. For every fixed x, you get a y of x. Let's say this is your decision variable. This is what you're allowed to play around with. The momentum is an independent variable in the Hamiltonian framework, right? In the canonical equations, you've seen that. So this is the Hamiltonian. Now instead of this y prime, you decided in your great wisdom to choose something else, some other numerical value, some other real value for that fixed x. So here's what we're doing, right? We are already trying to view this as some sort of an optimal control problem. Why so? Because you're sitting at x and you're trying to decide which way should you next head towards. That's given by the slope, the way you are heading. So if you choose this to be y prime along your optimal path, then this is the Hamiltonian. If you choose this to be some other slope, some other direction, right, what happens? Okay. So tell me, what is the Hamiltonian here for this? Sorry? Oh, sorry, I have to replace this with W, right? Sorry, thank you. Yes, silly me. Okay. So what is this? The dot product of, or okay, single variable, so dot product or product is the same thing. Y prime P minus L, let's be explicit, x, y, y prime. Yeah. What about this? Now y prime gets replaced by W, right? Yeah. So what is this? Rearranging the terms a bit. Let's write the momentum in its full glory, which is Ly prime. What is this? Seems familiar? What is this? Exactly this object, right? Of course, we don't need the bar anymore, we're just talking about a fixed x. You could substitute the x bar and so on. It's just one way of saying it's a fixed x. And if indeed y is an extremal, if it's a strong extrema, then this has to be greater than or equal to 0 by the condition we've just derived, isn't it? What does that tell us? This essentially means that whatever we have on that first line here, right? What does it mean? Standing at a point x on an optimal curve y evaluated at x, if you were to decide which direction you wish to travel to keep optimizing your function, you should choose the slope of the optimal curve. You should not deviate, you should not make any other choices, because once you do that, you are not going to be able to meet the conditions for a strong extrema. But more importantly, if this argument, the slope of the maximal, the extremal, were to be passed as the argument of the Hamiltonian, this actually maximizes the Hamiltonian. So viewed as a function of this third argument, because after all that's the only thing that's changed between these two. The momentum is an independent variable, remember, in the Hamiltonian framework. I repeat that at the cost of boring you. But the only thing that you're changing here is this. So if you want to maximize, if you want to get the strong extremal, you would want to maximize the Hamiltonian through a choice of this third argument. Go ahead and pick that as your third argument, which maximizes the Hamiltonian. Okay. That's a hint towards this. Of course, Weierstrass did not state his result or the implications of his excess function in this manner, because again, viewing it as independent variables, viewing those as independent variables was not in vogue back in the day. Okay. But the important thing is this. This has very, very crucial ramifications for optimal control framework, because our choices are invariably going to be linked with the dynamics, the control that we choose. Okay. So now, having derived this, we will for once and for all make this transition from x to t. Hereafter, our independent variable is going to be time throughout, not x, not a curve anymore, but trajectories in time. So we'll make this transition permanent now from x to t. Looks a little odd, especially when I write the next line, because now y of x will get replaced by x of t. So y prime of x will get replaced with x dot of t. As you all recognize this, if you have any familiarity with control systems at any point, these are things that we call as states in our dynamical system. Essentially, at the heart of it is some dynamical system x dot is equal to f t x u, with x at t naught being given by x naught. Yeah, x is an n tuple, of course. Once we understand this notation, immediately something should bother us a bit. What is it exactly that should bother us? Because we are used to looking at this L, x, y, y prime, and now in your minds you'll make this transition as L, t, x, x dot, right? That's the most logical thing to do. But we will not, however, be approaching this problem with this kind of a formulation. Rather, we shall be looking at it in the following manner. Can anyone tell me why? Or rather, how are we allowed to do this? Because it seems now if you are switching into this new mode, instead of x dot you have u, how is anything that we have derived thus far even relevant? Seems like a completely different formulation, or is it? Any ideas? Correct. You don't need to actually separate. Excellent. That's exactly the answer. Wherever you have x dot here, substitute f of t comma x comma u. So then again, this becomes further a function of tx here, and another, this is also dependent on t and x. So it gets absorbed within. So eventually it boils down to just a function of t, x and u. Of course, it might look like a different function to what it is. So you might, I mean, wherever you like, you call this a tilde. So call this a tilde and then call this back, I don't know, call this bar or something. It will not be exactly be the same function, no, because now the time and x related terms will enter through that function f, which is the vector field. Yeah. So this is reasonable, and this immediately makes a lot more sense to us from a control theoretic perspective, simply because after all, if you want to affect the states, you cannot just go ahead and manipulate x dot anyhow you like. If you think back on control systems lessons, the undergrad lessons that you learned, there's this whole notion of controllability and observability that you're familiar with. What's controllability after all? When back in the day they used to simulate the systems, they used op-amps. Now once you put those op-amps inside a circuit and put it in a box, outside the box, from outside the box, you don't have access to those individual op-amps. You only have a few channels, which are the input channels, through which you pass on certain signals, which in turn manipulate these op-amps to attain certain values or certain voltages. If you could access each op-amp individually, then you could change the states of each of those op-amps immediately without the need for any of these controllability or any of these associated notions. Similarly, if you could observe them, just read off the voltages at each individual op-amp and you have it, the entire picture of the circuit. But you cannot do that. There are only a certain legitimate channels that pop out of this box through which you can take measurements, and based on those measurements you are now going to infer about what the values of the states inside the box are. That's the observability question. So all of these important questions will start to become relevant here as well, because of course the way you choose your u is going to affect these states, and it better have, because if it doesn't affect the states, then there's no point, you're not driving the system anywhere, right, anywhere that you wish to. But at the same time, it's not as straightforward as choosing just the slope of the curve. You appreciate that, right? You're on a curve at a point and you decide which direction should I go, and you say turn to the left and immediately go to the left. Now you have a control system here, you have a dynamical system here. You want to go to the left, you have to turn the steering wheel, that has some latency, there are systems within, the steering wheel passes this on to the transmission channel, and then finally the wheel turns to a certain degree, the entire car moves afterwards. All the dynamics is encapsulated therein. So there is an inherent dynamics. It's not like you apply some u and immediately it reflects as x dot. That only happens if it's an integrator. X dot is equal to u. So you just replace x dot with u and it's the same thing. So you realize already what we have been looking at thus far translates readily to just a single integrator. If you have any dynamics that is slightly more complicated than a single integrator, it just falls flat from a control theoretic perspective. So we need to understand about this kind of a system a little closely. I will not go into details of the conditions for the existence and uniqueness of the solution of this kind of a differential equation. There are excellent books, two particular books that I can recommend from ODEs. One is by Coddington and Levinson, and the other is Birkhoff and Rota. Before we wind up today, I'll just very briefly touch upon what we expect out of this function f. We need to understand this f. If we want to understand how to solve this differential equation, okay, how to, as in at least qualitatively, at least be sure that starting from a particular t0 and an x0, you'll at least get a solution, and that the solution is unique, because if not, then you are in real trouble. So the least we expect from an ODE is that at least the fellow has a solution locally and that it is unique. Okay. So towards that end, we will set a few conditions, why those conditions are necessary, how they come about, and what are the details of those derivations. We will really not get into. The interested readers among you should refer to books, excellent books such as these. There are several other books as well. Yeah, you will see conditions such as Lipschitz, okay, Lipschitz continuity, and then there's the Bellman-Gronwall lemma, okay, Picard's iteration for ODEs. If you have done a course on ODE at an advanced level, you would be familiar with those ideas. But I will not go into those because that's beyond the scope of this course. I'll just say at this point on what we want this f to be in general. So typically if you look at a system which does not explicitly have the input here, maybe no external input applied, then for such systems we generally say that, well, with respect to T, f is piecewise continuous, and with respect to x, f is Lipschitz. Okay, you understand piecewise continuity. Lipschitz is just saying that, okay, if you start from a point t naught x naught, then within some neighborhood of t naught x naught you pick t1 x1 and t2 x2. Okay, then you can just say that f at t2 x2 minus f at t1 x1 divided by x2 minus x1. So these are all norms. Okay, if there are multiple tuples, then it's just a norm. You can just look at it this way. Yeah, less than or equal to some L. So this is the Lipschitz constant. Okay, so this helps in ensuring that, of course, a stronger assumption to invoke on this would be that it is continuously differentiable with respect to x. That, along with the application of a mean value theorem, would automatically lead to Lipschitz being true. Okay, so Lipschitz is one of the conditions that people do, but remember, we are talking about something more. We are talking about a situation where there is a control here that's also present. So for the most part, we will say that, well, with respect to this and this, we will expect continuity. Okay, yeah, I think that's it. Yeah, continuity with respect to this. With respect to this fellow, we will say, so these are different arguments, remember. So with respect to x, it is continuously differentiable. Now when you come to the derivative with respect to x, that's also going to be a function of t, x and u. Here we will again say that, okay, not only does the derivative exist because it is C1, but here also we will ask for some sort of a continuity. You could on occasions relax these assumptions. These are not all very hard and fast and tight conditions for existence of solutions. I am just saying these are the kind of things we will expect to impose on most cases. If we depart from this, we will make it clear. But apart from that, this is what it is. However, here is the deal, u of t need not be continuous in time. Okay, this is only piecewise continuous with respect to time. Okay, so you can have these jumps and discontinuities. Okay, so even though explicitly with respect to time, if you look at it, it's going to be continuous, but the u itself will introduce some sort of discontinuities. Also, the most crucial detail, the need for maximum principle, because as you will see towards the end of this chapter, we will come very close to something that appears like a proof of the maximum principle, but it is not. It is a little deceptive. What is that? This particular object need not exist. If it does, well, it's easy to see the maximum principle, it's easier to show the maximum principle. But the main power of maximum principle is that it's going to be calculus free. The proof is going to be free of calculus, it's going to be based on topology. Alright. So this is the crucial detail here. A lot of the times you will see that you will have dynamical systems where it's not necessary that this exists. Even in such situations, you will be able to apply the maximum principle, right. So this is the most important take home message from this discussion. When we come back next, we will see how we can look at the general structure of the cost functional to be minimized. Okay, there are specific forms. The specific form that we shall be looking at is the Bolza form of the cost functional, and then we will see that this Bolza form can be written purely as a complete running cost or as a complete terminal cost. The Bolza form has both a running cost and a terminal cost, but you can convert the running cost into terminal cost and vice versa. You can go from one to the other, and those will give rise to the Lagrange form and the Meyer form. So, we will see all of that, and then we will delve much deeper into these ideas, like how does a change in u reflect as a change in x. Earlier it was very easy, we perturb x by alpha g, x dot also gets perturbed by alpha g dot, but now this u does not show that very transparently. So, things are going to get involved, okay. So, we have to propagate the effect of a perturbation. In fact, now the perturbation will first have to be chosen in the u, because our choice variable is u. Does not make sense to consider a state that is proximal to the optimal state. There may not exist a control that takes you to that proximal state, and then in that case studying that as a legitimate candidate does not make sense. So, you will study controls that are adjacent or proximal to the so called optimal control, and then we will see how that affects the states, what sort of trajectories it shapes up eventually. So, that will require a further analysis which we shall indulge in next. Thank you.